will start in a few seconds. I want to welcome all in the audience, and especially I want to welcome you, Dan Rikoski, traveling the long way. I know you have had a bit problem to get used to the Danish time. On behalf of the Plantekongres and on behalf of the Danish Association for Conservation Agriculture, I want to invite you here, Don Rikoski. It is a pleasure for us. And to the audience, I will say that in the end, there will be time for some questions.
First of all, I thank the organizers for the opportunity to be here and talk a little bit about conservation agriculture and carbon management. I also would like to acknowledge the No-Till Farmers Association for their travel support. And I particularly want to acknowledge Bente for her translation of my PowerPoint and for her, all of her efforts in my travel arrangements. So it's very much appreciated. Briefly, with an outline on the next slide, I don't think I have to tell you too much about the need for carbon management, but I'm going to tell you anyway. I want to talk to you about plant carbon from a soil scientist perspective. Show you some of my research work on characterizing the tillage-induced carbon loss. Talk about the tillage impacts on carbon storage and on the greenhouse gas emissions, and then about carbon and ecosystem services. And hopefully you will get the impression that carbon is very important to us in our agricultural production systems. Next slide shows that there are three major problems that have been identified by FAO. World food security, the challenges of climate change, and the bioenergy production systems. And from my perspective, all three of those point to carbon. And they all can have some part of a solution that will start with better carbon management. When we talk about defining conservation agriculture, a very simple definition is intensifying crop production without intensifying tillage. FAO has a little more detailed definition, and I use the term no-till and conservation interchangeably. But there are three keys. One is minimum soil disturbance. The second is continuous crop residue cover. The third is diverse rotation and/or the use of cover crops. And I want to impress upon you that soil carbon is the foundation of all three of these principles. And hopefully you will get that sense of that as we go through the presentation. Next slide. We're interested in it because we have some environmental concerns on our planet. We're concerned about our children's future. And I think our one hope for solving some of these problems is in conservation agriculture. And so we have to understand that we're working with a living soil system. And that system depends on carbon because that's the primary energy source for the soil biology. And so we talk about soil organic matter, but the key chemical in that soil organic matter is carbon. Now this is an example of what intensive agriculture has done in some of the Midwest soils in the US. On the x-axis we have soil organic carbon versus time for two locations, one in Illinois and one in Missouri in the US. And you can see there's a continual decline in soil carbon that's been going on for the last 140, 150 years. You see some differences due to location, and you see some differences attributed to different types of cropping systems. So there are some clues there about what we might do to protect and preserve carbon. Part of the explanation for this difference in and the continued decline in soil carbon on the next slide is there's four possible explanations. And as a scientist, I have to be objective in terms of looking at other alternatives. But my bias is number one, the intensive tillage, that is the moldboard plow and the disc harrow, is responsible for a lot of the carbon decline that we saw on that previous map. But in our situation, we've changed from perennial species that put 60 to 90% of the biomass below ground to annual agronomic species that put only 15 to 20% of their biomass below ground. And as a result, we have a smaller carbon input into the soil system. The third factor that we have to consider is that we're using more nitrogen fertilizer, and nitrogen fertilizer enhances the mineralization or breakdown of the soil organic matter. The fourth thing identified by one of the colleagues is the increase in use of tile drainage in the Midwest creates a higher level of oxygen in the soil, and this results in more rapid oxidation of the organic matter. Each of these factors probably contributes, and I'm not sure which one is the primary explanation for that decline, but it does indicate that there are some things that we can do to perhaps make some changes in that, in trying to understand what's causing that. So the next slide shows the carbon cycle. We take carbon dioxide out of the air, combine it with water in the presence of light, and we capture some energy in the form of that sugar or the carbohydrate. The reverse of that process is taking the carbohydrate, combining it with oxygen, and useful energy is released during that process that we utilize in our everyday activities. Now, this is a very simplistic view of the carbon cycle, and as I indicate, the devil is in the details in terms of understanding that process. But one of the points I want to make is that the plants are the main source of our food and energy generation. And it's because of this process of photosynthesis that we're able to capture that carbon and eat the food and do the things that we do in our everyday activities. And so one of the things I hope I can impress upon you is that when you look at this maize plant, I want you to see carbon, because it is about 45 to 46% carbon. And so this plant is very valuable to us, and it has a lot of power in that it captures some of this carbon, it stores some of that carbon, it becomes one of our food sources, and with the biofuels, the corn stalks can be used as an energy source. And you can notice that the roots, in our case, they will go down to about 2 meters, and they're a form of carbon input into our soil systems. I'll talk to you a little bit more about some of the environmental benefits, but all of these add up to a better quality of life in our agricultural production systems. So when you see wheat or maize or winter rape or whatever crops that you're growing, I want you to look beyond the pretty plant and think about the carbon that's contained in that plant biomass. The reason is that the true soil conservation is more related to plant management than to soil management, because the plants provide this carbon from the atmosphere to the soil. And that's why plant management, in effect, is carbon management, and that's why it's important for us to try to maintain some sort of an optimum carbon management. Without that, plants, we're not going to do very much conservation. And as a soil scientist, this was hard to admit, but after 40 years, you see things a little differently. So, when we look at this picture, if you take nothing else home from this presentation, I want you to understand that carbon is the C that starts conservation. And if I had time, I would repeat it for emphasis. But if you look at the plants on the left, the contour strips, they're there to protect the soil from erosion, and they are 40 to 50% carbon. In the grass waterway, the grass is there to provide a protective coating to minimize erosion when we have runoff, and those grass species are 40 to 50% carbon. In our no-till systems, we have crop residues on the surface, and again, those are very important forms of carbon that we must understand. And so we in agriculture, I think, have a responsibility about managing this carbon as best we can. And I think that when we do this conservation agriculture, this can be our small step in contributing to trying to combat climate change. Now, this carbon is important to us, next slide, in terms of being the center of what I call the soil magic triangle. There's biological, physical, and chemical processes and properties in the soil that are important to us. And all of these are somehow indirectly or directly related to the carbon that's in the system. From a biological perspective, it's the primary energy source for the little critters in the soil. From a chemical perspective, it can enhance the cation exchange capacity by contributing in that regard. In the physical properties, it will also help to decrease the bulk density and increase the water holding capacity. So from managing the soil perspective, carbon is very important to us in terms of what it applies to and what we can do to change some of those properties. Now, in an agricultural production system, the farmer is working with the resources. I count the sun as a resource because without it, we wouldn't have photosynthesis. But the farmer takes the sun, the air, the water, and the soil to provide these ecosystem services. Food, feed, fiber, and now biofuel is an example of these ecosystem services. And so, from my perspective, all of these ecosystem services are provided or driven by the carbon cycle. And that's why it's very important to us in terms of maintaining food security and all those other ecosystem services that are provided. So now I'd like to switch a little bit to some of my research characterizing the tillage-induced carbon dioxide loss from the soil. And on the left-hand side of the picture, you see these flickering flames, and they're there to represent a slow oxidation of the organic matter. When you open the soil up with a tillage event, you have 21% oxygen going into the soil, and you get this rapid oxidation of the organic matter. This is analogous to pouring gasoline on a fire. So that carbon is burnt out of there very rapidly. Now, you understand that carbon dioxide is colorless, it's odorless, and tasteless. So you cannot perceive that there's a problem. But I will try to convince you that there's a cloud of carbon dioxide the size of that cloud of dust. With that cloud of dust, you can see that dust, you can feel that dust, you can taste it, and you can perceive that there's a problem. And so we will try and demonstrate with some data to show you that there is a large burp of carbon dioxide that comes out of the soil as a result of intensive tillage. Intensive tillage does a lot to disrupt some of the natural cycles. The big three that we manage in agriculture are the water, the carbon, and the nitrogen cycle. And so this intensive tillage, when it disrupts one, and I'm just going to talk to you about the carbon cycle, but it impacts the water and the nitrogen cycle. And so this impact affects all these properties and processes that we've talked about, and we have to understand what is happening in that system as a result of intensive tillage. And so I'm going to focus on the carbon part in terms of some of my research. We developed this mobile research gas exchange machine, which is nothing more than a large plastic box mounted on the front end of a forklift, and we have some fans in there stirring the air to get a uniform concentration, and then we take a sample back through the tube and run it through an infrared gas analyzer to measure the carbon dioxide and water vapor concentration once a second for 60 seconds. At the end of that period, the computer beeps at the operator, he lifts the chamber, and he moves to the next location. And during that time, the flux of carbon dioxide and water vapor is calculated. And so I'm trying to use some plumes from our local ethanol plant to give you a sense of the physical process that we're trying to characterize. You recall I said that carbon dioxide was invisible. And so I'm trying to give you a physical picture of what's happening in terms of gas exchange. And so this effort is to try to characterize those invisible effect of invisible forces that are very difficult to describe to people at times, and we are challenged in terms of trying to get people to understand the magnitude of the problem when they can't see it, feel it, or touch it. So we set up a study to look at various types of tillage on the tillage-induced carbon dioxide loss. On the left-hand side, we had what we call our no-till plot. We ran the tractor through the plot to get the same amount of wheel compaction on all of the treatments. Then we had a small volume of soil disturbed with a very shallow strip tillage that was accomplished through the use of a fluted coulter. We had the V-shaped zone with a fertilizer knife that went to 150 millimeters deep with the approximate shape that you see there. We had a second fertilizer knife, the next slide, on the left-hand side that gave more a U-shaped volume of soil disturbance. In the middle, we had what we called a low disturbance subsoil shank that gave a very narrow trench of loosened soil down to 350 millimeters deep. And then we compared that to the moldboard plow to a depth of 250 millimeters. And so these are the 6 types of tillage that we evaluated in looking at the carbon dioxide loss. So when we take a look at the yield results, on the y-axis is the cumulative loss for a 5-hour period on the left-hand side and a 24-hour period on the right-hand side. And the initials on the x-axis represent the moldboard plow, the subsoil shank, the fertilizer knife, and then clear over to the extreme is the no-till treatment. And you can see that in both cases, the moldboard plow gives us the largest amount of carbon dioxide released, followed by the subsoil shank. Various forms of strip tillage showed a decline with the minimum loss of carbon dioxide from the no-till treatment. So if you start to think about it a little bit, we repeated as many times and we get basically the same types of relationship. And so if we take a look at the cross-sectional area from those schematics that I gave you and assume a unit length of row, we have a volume of soil that's disturbed by the tillage operation. And so we've done that, and we plot the next slide, the cumulative loss on the y-axis. There we go. Cumulative loss on the y-axis and the cross-sectional area, or the equivalent of the soil volume, on the y-axis. And you can see at the top, the moldboard plow has the largest amount of CO2 released. The subsoil shank is in there. The various forms of strip tillage are in there. And with the no-till, we get the least amount of carbon dioxide. And if we do a simple linear regression, it doesn't show on the slide, but in my slide it shows an R-squared of about 0.97, a good linear relationship. The results suggest that the carbon dioxide released is proportional to the volume of soil disturbed. Now, for those of you who are farmers and drive a tractor, you'll know that the amount of diesel required is much greater for the moldboard plow treatment than for the no-till treatment or other forms of strip tillage. So from my perspective, intensive tillage becomes a double negative. The carbon loss from the soil and the additional carbon going back to the atmosphere of CO2 from the consumption of a large amount of diesel fuel. We did a second study, this time using the same implement, the moldboard plow, to allow us to get different volumes of soil disturbed. The upper one was 100 millimeters deep. It was shallow as we could go and still call it inversion tillage, represented by the moldboard plow. We went through 2 intermediate depths and to a depth of 280 millimeters, which is as deep as we could go and pull it with the tractor that we had. So we have the same piece of equipment, but different volumes of soil disturbed. When we take a look at the cumulative results for a 24-hour period, next slide, you can see that with the no-till treatment, we have the least amount of CO2 lost. And as you go progressively deeper from 100 millimeters to 280 millimeters, there's approximately a linear increase in the amount of CO2 that's released. Another bit of evidence that the CO2 released is proportional to the volume of soil disturbed in the tillage operation. So we wanted to take this to the extreme, and I had an opportunity to go to a farmer field day and evaluate two different no-till drills. And they're defined as no-till drills by the manufacturer. This is one of the examples, and it happens to be in South Dakota where they do things in a big way. And so we were able to, we had this opportunity and wanted to evaluate the CO2 and the water vapor loss from these two no-till drills. On the left-hand side, on the next slide, we have what I call a low disturbance drill with a double disc opener that just basically cuts a slot and drops the seed in. On the right-hand side is what I call a tine opener, and results in a high disturbance no-till drill. And if you take a look at the surface, you can see that there's much more of the wheat residue on the surface with the low disturbance than with the high disturbance drills. And even with them having packing wheels to reconsolidate the soil, we were able to measure some differences in that. But if we take a look at it from the broad view and the broad perspective, on the extreme left-hand side, there's a non-disturbed area where there was nothing done to it. But then we went through there with the one pass with the low disturbance drill, followed by the high disturbance drill, a disc harrow, and the moldboard plow. And so you can see over a large section the relative difference in the soil mixing and the incorporation of the crop residue, even though they're both considered no-till drills. So when you look at the data from that, with a few measurements, on the left-hand side is carbon dioxide loss, and on the right hand is evaporation rate expressed in millimeters per hour. So where there was no disturbance, you can see the numbers where we got relatively small amounts of water vapor and carbon dioxide loss. With the low disturbance drill, represented by the bars in the middle, there was virtually no difference in the carbon dioxide and a slight increase in the water vapor. But with a high disturbance drill, you see both of them increase substantially above the low disturbance drill and the control condition. Again, so what that, well, it was gratifying to me because it reassured that the technology that we're using with that portable chamber was sensitive enough to pick up some of these very small differences. And I'm happy that it came out this way, but I want to reassure you that even with this high disturbance drill, that is nothing very close to what we get with the moldboard plow and other forms of intensive tillage. But the principle is the same. If you want to minimize carbon loss, you have to minimize the volume of soil disturbed. So tillage makes this gas exchange happen. And I think that now that we understand that, it's changed my thinking a little bit, that we must try to find better ways to manage the soil. So now I was asked to talk a little bit about carbon sequestration, the next slide. And I find that I have too much information on the slide to present it in the time that it was allotted. And so I'm going to give you a one-sentence statement about each of the slides, which is my summarization of it. And if you want to talk about it in more detail, I'll be happy to visit with you after the presentation. One of my colleagues in St. Paul, Minnesota, is John Baker and his co-authors. They found that there was really no difference in carbon sequestration with no-till compared to conventional till when they sampled to 1 meter depth. That's just the way it is. There was no statistical difference. Another example of a similar finding by Ratan Lal and some of his colleagues from Ohio State. They found that the no-till impacts were soil-specific, but they found no difference in the accumulation of carbon between the no-till and the conventional till to a depth of 60 centimeters that they sampled. The next slide shows some work by Christopher et al. They found that the sampling depths effects were important in terms of trying to quantify the carbon, but they, again, could not find any difference in the carbon sequestered between the no-till and the conventional till system down to 60 centimeters. The next slide shows a fourth example of some work from Verda in 2011, and they were able to show that there was greater carbon in the surface layers of the no-till relative to the conventional till, but there was no difference in the carbon between 30 and 60 centimeters. And they also verified that there was a tremendous amount of variability in that subsoil depth that contributed to the lack of statistical significance when you looked at the carbon in the entire profile. And that is a significant finding because when people are making some of these comparisons, when you have 2 or 3 times the variability within the profile, it makes it difficult to interpret. So there's a lot of data that suggests there's no difference, but I think there's other ecosystem services that are important to us that we need to reevaluate it, and we're in a process of trying to identify specifically the type of equipment they were using, the speed of the operation, to see if there's some clue about the details that prevents the no-till from having any more carbon sequestration. So on the next slide, we make a point about why we're interested in carbon dioxide. Our Energy Information Agency in the U.S. have shown that carbon dioxide is responsible for about 81% of the global greenhouse effect. So it's one of the reasons that I'm interested in following the carbon dioxide. And so it's why I continue to do that. But we must understand that there are other greenhouse gases that are important to us. The concept of global warming potential with methane has a global warming potential of 21, and nitrous oxide has a global warming potential of about 296. Well, methane's a problem with cattle production, but nitrous oxide is a problem with also animal production and the use of nitrogen fertilizer. And so I have 2 examples of what some of the scientists have found in the US and Canada on nitrous oxide. This is Philip Rochette and his colleagues from Canada, and they found that there was the nitrous oxide emissions in the no-till system depend on the soil type. And what they found with a heavier soil, with a high clay content, there was more nitrous oxide emissions from that soil as opposed to a well-drained, gravelly loam. Some of the people in the next slide, at Purdue University, Amanandi et al. In 2011, they found that 50% of the nitrous oxide emission occurs shortly after the application of the fertilizer. And then that the no-till emissions were lower from the no-till than the conventional till, but it was not statistically significant. And as you might expect, there's a lot of variation in that. So we're promoting no-till, but we're not out of the woods in terms of what it means in terms of the greenhouse gases. And there's a lot more research that needs to be done, and I think that we have to be careful in terms of what kind of recommendations we make, and hopefully that we can do our homework before we make claims about what no-till does for all of the greenhouse gases.